Hello and welcome to Lesson 30 of Additional Maths with Mr. Barrow. Today we're going to be looking at reduction to linear form, the second part. In Lesson 29 we looked at how to turn exponential and polynomial functions into graphs that you can model with a linear function by changing the scales and using logarithmic scales. Today we're going to look at an actual situation where we've got some data which looks like it might follow an exponential curve, and that we are going to plot it using a logarithmic function and answer some other questions along the way. So let's look at this first question. The area of a Petri dish in millimeters squared, which is covered by bacteria after T hours, is measured. Okay, so we want to know how much of the Petri dish is covered by the bacteria, and it'll grow over time as the bacteria replicate. So we have some data here that after 1 hour, there's 12.1 millimeters squared of the Petri dish which is covered. After 2 hours, 17.9, etc. Okay. A bacteriologist believes there's an exponential relationship given by A equals KB to the power of T, where A is the area, T is the time in hours, and K and B are just constants that we need to determine at some other point. So the bacteriologist just believes there is some exponential relationship between A and T. And the bacteriologist wants to know what that relationship is so they can predict future areas covered by the bacteria. If they know the time, they can predict the area because they know the equation. So the questions we're going to answer are the following. Firstly, we're going to write A equals KB to the power of T in linear form, following the same process we did in the last lesson. We're then going to plot a graph with a logarithmic scale. So with log A, it's the y-axis against T at the x-axis. And we're going to use that to explain why the graph supports the bacteriologist's belief that there is some exponential relationship. We're then going to use the graph to estimate the values of log B and log K and find these constants K and B so that we can then predict some other values. We're going to then use it to estimate the area after 12 hours and the time taken to cover the whole Petri dish, which has an area of 30,000 millimeters squared. Okay, so let's start with the first part. Write A equals KB to the power of T in linear form. So, using our process from last lesson, we know that A equals KB to the power of T can be rewritten in linear form by using logarithms. So we can take log of both sides. So log of A is equal to log of KB to the power of T. And therefore we can split up the log on the right side. So log A is equal to log of K plus log of B to the power of T, and using the third log law, that becomes T log B. So now we have it in a form which is a linear form. So this is of the form y equals mx plus c, where the y is log A, so that will be our y-axis. The c is log k. We don't know what k is, but it's a constant, so log k will be just some number. T will be our x-axis, and log b will be the gradient of our graph. So now we're going to plot a graph of log A against T using the data we've got. And we're going to show why the graph supports the bacteriologist's belief. When we plot it, we get a straight line, then it'll support the bacteriologist's belief, because if we plot log A against T and it forms a straight line, then that shows that the exponential is turned into a linear graph by using this method, this reduction to linear form. And so if we have log A against T and it forms a linear graph, then we know it came from an exponential function. So let's do that second part. Plot the graph of log A against t. Well, we have the values of A for every value of t. What we do now is we've got to create an extra row. We want to plot log A, not A. Okay? So for each value of A, we need to find log of A. We don't need to be extremely accurate. We'll get lots of decimal values on our calculator. So we do log of 12.1, and we're going to put it to 2 decimal places, 1.08. 1 decimal place would probably be fine, but I'm going to write it to 2 decimal places for each one. Log of 17.9 is 1.25. Remember, when we say log of, we're doing log base 10. That's our default logarithm. 1.43 is the next one. 1.60. 1.78. And 1.96. So those are the values of log A. So we're going to plot log A against t. So we're going to plot coordinates where we go across by the t value and up by the log A value. And here is one I prepared earlier. Ta-da! So here is the graph of log A against t. As you can see, this coordinate here is 1 across and 1.08 up. So it's this bit of information from our table. Okay, plotting log A against t. And then as I've done, I've plotted all the other points. Okay, so let's see, does this form a straight line? It does seem to. So let's try and draw a straight line through those points as best we can. I'll try and do that. So I get something like this. There's my straight line. Okay. So it does seem to follow a straight line, and hence part 3, which says use your graph to, so part 2, which says explain why your graph supports the bacteriologist's belief. Well, when we plot it with a logarithmic scale, it forms a straight line, and hence it must have been an exponential curve on the original graph. Okay, so it does support the bacteriologist's belief that there is some exponential relationship between A and T. So next, use your graph to estimate log B and log K, and hence B and K. All right, so this graph should have an equation. Log A is equal to log of K plus T times log of B. Now we know that this follows a similar form as y equals C plus x times m, or mx plus c, but in a different order. So the c seems to match up with log k, and the m matches up with log b. So if I know the y-intercept of my straight line, that will be what log k is equal to. If I know the gradient of this straight line, that will be what log b is equal to. So all I need to do is find the y-intercept and the gradient, and I've got log k and log b. And then I can work out k and b. So let's do a little bit of work on the graph. My y-intercept looks like it's about 0.9. So that means log k must be 0.9, since log k was our y-intercept. Next, log b is the gradient. Well, the best way to do gradients is to take 2 points relatively far apart and draw a triangle and do the change in y divided by the change in x. So here, I'll take this point because I know where this point is. I know it's at 1.08. This point here is the point 6, 1.96. Okay, so we have 6, 1.96 there, and we have 1, 1.08 here. The change in x is 5. Between 6 and 1, the change in x is 5. The change in y between 1.96 and 1.08, it's gone up by 0.88. So therefore, the gradient, which is log b, so log b is equal to the change in y, 0.88, divided by the change in x, 5. So that there is 0.176. Okay. So we have log b. So it's approximately 0.176. By the way, these are approximations. These are estimates because we're reading off from the graph, and I'm also using 2 points which are not necessarily exactly on a straight line, because these points don't follow a perfect straight line. They're very close to it. They do look pretty good, but they might not be perfectly on a straight line. But it looks like a good estimate is this 0.176 for our gradient. That for every one we go across in time, we go up 0.176 for log A. Okay, so we have log K and we have log B. Hence, we need to find K and B. Okay, so let's work with our logs. If we know that log K is equal to 0.9, that means log base 10 of K is 0.9. That means that K will equal 10 to the power of 0.9. which is 7.94. So that comes directly from this expression. If log k is 0.9, then k will be 10 to the power of 0.9. Similarly for b, if log b is 0.176, then b will be 10 to the power of 0.176, which is 1.50 to, and both of these are just to 3 significant figures. So we've done this question now. We've done this part. We found the value of b and the value of k. But a good idea would be to rewrite the bacteriologist's formula with these values. So our model for the data, which the bacteriologist thought would be a equals kb to the power of t, we can now write with those actual values. So a is equal to 7.94 multiplied by 1.50 to the power of t, approximately. So that is now our equation that links a and t. It means really probably that it started, when we started timing the process, it started with an area of 7.94 millimeters squared, and that every hour it'll increase by 50%. If we're multiplying by 1.5 for every unit of time, it'll increase by 50% every unit of time. Okay, so now we're going to use that for the next part. So estimate the area after 12 hours. Okay, well that's relatively simple. We've got an equation. So area equals 7.94 times 1.50 to the power of t. So when t is 12, the area is equal to 7.94 times 1.50 to the power of 12. So this is, again, remember this is an estimate because we are we've done some estimations to create these relationships, and that gives us 1,030 millimeters squared to 3 significant figures. So just over 1,000 millimeters squared are going to be covered 12 hours later, after the start. And part B, what's the time that's going to take to cover the entire 30,000 millimeter square Petri dish? So here, I don't know t, but I know a, and I need to now solve to find t when a is 30,000. So I substitute 30,000 instead of a in the equation. So 30,000 equals 7.94 multiplied by 1.50 to the power of t. Next, I try and solve this, I need to use logarithms to solve it. But first, I'm going to divide by 7.94. If I divide both sides by 7.94, I get 3,778-ish, 0.3 ... is equal to 1.50 to the power of t. Therefore, using my knowledge of logarithms, I know that t is log base 1.50 of 3,778.3 ... And that is 20.3 to 3 significant figures. So 20.3 hours later, after the start of the experiment, my Petri dish is completely covered. So, running through all the different processes in this question, if we think that there is an exponential relationship, we can rewrite that exponential relationship in linear form and plot the graph of the information with a logarithmic scale. So instead of plotting t against a, we plot t against log a. If it forms a straight line, then that means the original relationship was exponential. We can then find the gradient of that straight line and the y-intercept of that straight line, and those values will help us find the constants in our exponential relationship. And we can then use our new function, our new formula, to predict future values. Okay. Have a go at this question. I got a little bit distressed last April. There was a slight ant infestation in my house. And so let's say I measured the number of ants, I counted the number of ants in the entire house. And here was the data. So T days into April 2020, there were these many ants in my house. I thought at the time that they were growing exponentially. Luckily, that wasn't the case. Otherwise, I'd be completely overrun by now. I want you to write this relationship, which I believe is the number of ants is some constant k times another constant to the power of t. I want you to write that relationship in linear form, then plot log of n against t and explain why I might be correct. Then use your graph to estimate log b and log k and hence b and k. Then use that new formula that you've created, so this formula here, but with the values of k and b found, use that to find how many ants there would be on day 8, or to estimate how many ants there would be on day 8, and estimate how long until I give in and leave my house. Okay, so 1 million ants will push me over the edge and will mean that I leave and never come back. Luckily, that didn't happen. So have a go at that, pause the video, and then I'll show you the answer. Okay, so if you've answered this right, here's the correct answer. Firstly, to put it in linear form, you get log n equals log k plus t log b. Then, to plot it, you need an extra row of your table for log n. And those values are 1.20, 1.63, 2.11, 2.60, 3.10, 3.57. If you then plot those on a graph, you get a graph log n against t, you get a pretty good straight line, where the y-intercept is around 0.7, and the gradient is, well, it goes 2.37 up for 5 across, so a good estimate for the gradient is around 0.474, something around 0.48. So when you then do your calculations to find k and b, k is around 5. I got 5.01, but anything around 5 is fine. B is around 2.98. I got 2.98. Anything around 3 is fine. Okay. So therefore, your function for the number of ants is approximately 5.01 times 2.98 to the power of t. That seems to indicate that every day the number of ants will triple. Okay. 5 times 3 to the power of t is fine if you got that instead, okay? Because it's only an estimate. We're judging various things, so it's okay to round it a little bit more. Then, once you've got that, if you want to find out how many ants there are on day 8, you plug 8 into that and you get about 31,200 ants using my function 5.01 and 2.98, but 32,800 if you used 5 and 3. And then solving the equation to find out how long it takes for there to be 1 million ants. Using my function, it was 11.2 days. Using the simplified function, it's 11.1 days before I leave. Okay, if you got all that, that is fantastic. This is not easy, okay? But practice this process and you will get a lot better. So what you should do now, first, congratulate yourself, okay? Pat yourself on the back. Don't hail the ant overlords. What you should do now is go to the textbook and have a go at exercise 12.3. So the third exercise in chapter 12. And this question 3 onwards will help practice this process of getting some data and plotting it as a straight line, as a linear function on a logarithmic scaled graph. Okay. In the next lesson, we'll go on to the next chapter, chapter 13, where we're going to be starting to think about numerical methods of solving equations and various things. Things like iteration, the trapezium rule, things like that. Okay, so off you go and enjoy this, and I will see you in the next lesson.